Okay, we are recording. So I'm going to start with a small lecture and we will go through exercises. The first homework is there. So it is on Canvas. You can start it. You don't have to do it in one sitting. I think we don't have all the theoretical background to complete it totally for now, but you can do most of the question already. So you can go on Canvas and start homework number 1 and save it, and you can come back some days after. I will specify the due date very soon as we cover all the theoretical topic that we need for you to complete homework number 1. Okay, so as I was saying, I'm going to I'm going to start a small lecture, and we are going to talk about subnetting again. So there is something that we call the magic number. So the magic number, we obtain the magic number from a net mask. So let's say that we have this net mask /25. /25 is 25, 1, no? So 8 plus 8 plus 8 plus 1 will be 25, 1. So to get the magic number, you find the last one. And the value of this last one will be the magic number. So the last one in the series of 1 is this one. And this one is 128. So the magic number for this mask will be 128, and it is in the 4th byte. Let's say that we have this mask, /26. /26 is 26, 1. 8 plus 8 plus 8 plus 2. The last one is this one. Its value is 64. So the magic number will be 64, and it is in the 4th byte. Let's say that we have this net mask, /27. It's 27, 1, so 8 plus 8 plus 8 plus 3. The last one is here in the 4th byte. And the value of this last one is 32. So the magic number for this net mask will be 32. And it is in the 4th byte. There is another way to compute the magic number where you don't have to pass in binary. So what you will do, you will look at the dotted decimal notation of the net mask, and you will scan the net mask from left to right in search of the last byte that is not 0. So the last byte that is not 0 here is the 3rd byte, because after we have a 0. And to get the magic number, we will always do 256 minus this value. So 256 minus 240 will be 16. So for this net mask, the magic number is 16, and it is in the 3rd byte. Let's see another example. So for example, we have this net mask /18, which is 8 plus 8 plus 2, isn't it? So I'm going to parse the net mask from left to right in search of the last byte that is not 0. This is this byte, 192. This is the last byte that is not 0. So the magic number will be 256 minus this last byte. It's giving me 64. And the magic number is here in the 3rd byte. Let's take this example, /14. So 14 is 8 plus 6. So here we have 6, 1, no? So to get the magic number associated with this net mask, I'm going to parse the net mask from left to right in search of the last byte that is not 0. So the last byte that is not 0 is this 252. So the magic number will be 256 minus 252. It's giving me 4. And this magic number is in the 2nd byte. Okay? So the magic number can be in the 2nd byte, in the 3rd byte, in the 4th byte. For example, here the magic number is in the 4th byte. Here is in the 2nd byte. Here the magic number is in the 3rd byte. So you will always do 256 minus the last byte that is not 0. Okay? Okay, so the magic number, as the name say, it's magic. It will allow us to get the subnet information very fast in a magic way. So let's say that you have this network at the beginning, 192.168.103.0/24. And you want to divide this network in 8 subnetworks of the same size. So if you want to divide in 8 subnetworks, how many bits you need to borrow from the host part and convert them to a subnet part? 3 bits. Okay, if I borrow 1 bit, I can create 2 subnetworks. If I borrow 2 bits, I can create 4 subnetworks. If I borrow 3 bits, I can create 8 subnetworks. So I will go, the initial pattern was capital N, capital N, capital N, capital H, which means that the 8 bits that are here belong to the network part, the 8 bits that are here belong to the network part, the 8 bits that are here belong to the network part, and the 8 bits that are here belong to the host part. So in the host part, we are going to borrow 3 bits and convert them from H to S. H for host part, S for subnet. So the pattern will be 24 bits of network, 3 bits of subnet, and 5 bits of host. So the subnetwork mask, at the beginning, the network mask have 24.1. Since I borrow 3 bits, I go to 27. 24 plus 3 is 27. So the new network mask is 255, 255, 255, 224. Let's compute the magic number. So I'm going to parse this network mask from left to right in search of the last byte that is not 0. This is the last byte that is not 0. So 256 minus 224 will be what? Will be 32, no? So the magic number is 32, and the magic number is in the 4th byte, which means when I'm going to create the 8th subnetwork, what I can do is the last byte I start in 0, and I go by step of 32. So 0 plus 32 is 32. 32 plus 32 is 64. 64 plus 32 is 96. 96 plus 32 is 128. 128 plus 32 is 160. 160 plus 32 is 192. 192 plus 32 is 224. So that will be the information of the subnet. When I know the subnet, it is very easy for me to get all the information, which is the net mask, the network address, sorry, the broadcast address, the first valid IP address, and the last valid IP address, no? So look at how it's easy to get the information of all the subnet with the magic number. The magic number will give me 2 information, a byte, here the 4th byte, and an increment. So in the 4th byte, I have to go by step of 32. And I get all the subnetwork, all the 8 subnetwork without having to go to binary. But if I go to binary, we have 3 bits that belong to the subnet part. And of course, we have 8 possibilities. And those are the 8 possibilities, 0, 0, 0, 0, 0, 1, up to 1, 1, 1. So of course, this SSS in 0, 0, 0 correspond to the to the first subnetwork, which is subnet number 0. And this will be the subnet in question. For example, this SSS in 001 correspond to the second subnet, or subnet number 1, because this is 1. And this will be the network. So we have the network address, and we have the subnet mask, no? To identify the network. Let's see another example. Let's say that initially you have this network, which is a class B network, 172.16.0.0/16. And I want to divide this network is 128 subnetwork. So if I want to do 128 subnetwork, how many bits I need to borrow from the host part and to change them to subnet bit, so I can create the 128 subnet. I need to borrow 7, no? If you borrow 1 bit, 2 subnetwork. If you borrow 2 bits, 4 subnetwork. If you borrow 3 bits, 8. 4 bits, 16. 5 bits, 32 subnetwork. 6 bits, 64 subnetwork. 7 bits, 128 subnetwork. So you need to borrow 7 bits. So look at here, before I did the subnet, all those were host bits. Okay, because it's a /16, which means that we have 16 network bits, and at the beginning, 16 host bits. I'm going to borrow 7 bits on the host part and convert them to subnet part. So that will be the pattern of the IP addresses. So the net mask that was 11111 up to here, now arrive up to here. So if it arrives up to here, it will be 255.255.254.0. So this is the subnet mask. All the 128 subnet will have the same subnet mask. So to go faster, instead of working with binary, we can work with the magic number. So let's compute the magic number associated with this net mask. So for that, I'm going to parse the subnet mask from left to right in search of the last byte that is not 0. It is there. And the magic number is always 256 minus this value. So 256 minus 254 will be 2. So I need to go by step of 2 in the third byte. So look, I start in 172.16.0.0. And in the third byte, I go by step of 2. So 0 plus 2 will be 2. 2 plus 2 will be 4. 4 plus 2 will be 6. Blah, 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 blah. Up to the last subnetwork. Okay? For example, here, this is 2 network to the last is 250. 250 plus 2 is 254, 252. 252 plus 2 is 254. Look, if you do 254 plus 2, you get 256. We cannot have 256. Okay, we can have up to 255. So it's why we don't have more after this one. This is the last one. This will be subnet number 127. Okay, subnet number 127, where the 7 bits of S are in 1. Okay? Okay, let's say that you need to configure this network. So in this network, we have a router. Each interface of the router represents a different network. So here we have a network, and here we have a second network. So if initially they give me this network, 192.168.10/24, and I need 2 subnetworks. I need to divide this network into subnetworks. So I can assign one subnetwork here and another subnetwork for those devices that are here. So I need to borrow 1 bit. And if you borrow 1 bit, the new net mask will be /25, which is 255, 255, 255, 128. And if you like the magic number will be 128, which means that you will have two networks, one that starts in .0 and the other one that starts in .128. And this is what we see here. So in this network, we put the first subnetwork, which is 192.168.10/25. And here, we put the second subnetwork, which is 192.168.128/25. So remember, at the level of a router, each interface represents a different network. So when you do subnetting, for each interface of the router, you need to think about a subnet. So this will have a subnet, and this will have a different subnet. Okay, we have not seen how to configure Cisco router devices, but those are the commands that we will use in some classes from now when we configure a Cisco router device. So for example, this router R1 have a gigabit Ethernet interface, which is called gigabit Ethernet 0/0. And in this interface, we will put the IP address 192.168.1.1. So this command says that in the gigabit Ethernet interface 0/0, we want this IP address 192.168.1.1. And the net mask is a /25. Here we wrote the net mask in the dotted decimal notation, which is 255, 255, 255, 128. And in this interface, which is gigabit Ethernet 0/1, we are going to put this IP address, which is 192.168.1.129. So as you can see, there is a command that is called IP address. I specify the IP address that I want and the net mask that I want for this network. Okay, we will come back on that, how to configure router Cisco devices in the future. Okay, so look, how do I compute the total number of subnets? So if you borrow n bits from the host part and convert them to the subnet part, the total number of subnets will be 2 to the power of n, which means that if you borrow 3 bits, 2 to the power of 3 is 8, so 8 subnetwork. If you borrow 5 bits, 2 to the power of 5 is 32, so 32 subnetwork. So the formula that we are using to know the number of subnet is 2 to the power of number of bits that I borrow from the host part to the subnet to create subnets, no? So here they say, if you borrow 1 bit, 2 subnetwork. For example, here you borrow this bit and you convert it from a H to a S, you can create 2 subnetwork. If you borrow 2 bits, 4 subnetwork. If you borrow 3 bits, 8 subnetwork. It's 2 to the power of number of bits that you have borrowed. Now, how do I compute the number of valid IP address? So it depends on the host part. It depends on the number of bits that I have in the host part. But it will be 2 to the power of the number of bits that I have in the host part minus 2. Why minus 2? Because we lose 2 IP addresses in a network. The first IP address and the last IP address. Remember that the first IP address is the network address and the last IP address is the broadcast address. So it will be 2 to the power of number of bits in the host part minus 2, because we lose 2 IP addresses. So for example, here, if you have 7 bits for the host part, how many valid IP address you can create? It will be 2 to the 7 minus 2. And 2 to the 7 is 128. 128 minus 2 is 126. So you can create you will have, sorry, in the network or the subnetwork, you will have 126 valid IP addresses or host IP addresses or usable IP addresses. No, those are terms that are exactly the same one. Okay, let's say that initially I have this network 192.168.10/24, and I want to divide this network in subnets such I can assign IP addresses to those devices. So how many subnets do we need if we want to assign IP address to those devices that are here? So what we have to look is the router. So this router, each interface of this router should be a different subnet. So this interface will be one subnet. This interface will be another subnet. And this interface will be a third subnet. So if I want to divide the original network into subnets, I need to create 3 subnets. We cannot create exactly 3 subnets. What we can create is 2 subnets, or 4 subnets, or 8, or 16. So what will be the most adequate number? We need 3, but we cannot create 3 exactly. So we can do what? We can do 4. If I do 4, I need to borrow 2 bits. So what you can see here, they borrowed 2 bits, and those 2 bits were converted to subnet bits. Okay, if I borrow 2 bits, I go from a /24 to a /26. And the /26 is 255, 255, 255, 192. What is the magic number? So I'm going to pass this network mask from left to right in search of the last byte that is not 0. And this last byte that is not 0 is 192. So 256 minus 192 is 64. So the magic number is 64, and it is in the 4th byte. So to get the subnet, I will start in 192.168.10, which is there. And in the 4th byte, I'm going to go by step of 64, because the magic number is 64. So 0 plus 64 is 64. That will be the second subnet. 64 plus 64 is 128. That will be the third subnet. And 110.28 plus 64 is 192. That will be the 4th subnet. If I try to continue, look at what we're going to happen. 122 plus 64 is 256. I cannot have 256. So it's means that there is no more subnet. So now I have 4 subnets, and I can map them here. For example, here, they took the first subnet and they put it here. Okay? They took the second subnet and they put it here. And they took the third subnet and they put it here. We have a third network here. And this one is a spare subnet, which means that if the company grows in the future, we still have a subnet that is free. So if we create a new department and we need a new subnet, we already have one in spare, as you can see. Okay? Which is the 4th subnet, 192.168.1. 192/26 is a spare subnet. If I ask you how many IP addresses in total we have in each subnet, so the host part have 6 bits. So it will be 2 to the power of 6. And 2 to the power of 6 is 64. It's why I go by step of 64. There are 64 IP addresses in each subnet. Now, valid IP addresses will be 64 minus 2, which is there. And 64 minus 2 is 62. So we have 62 host IP addresses in total, or valid IP addresses, or usable IP addresses in each subnetwork. Okay, so this is the same example as the previous one. We started with network 192.168.1.0, and we need to create 3 subnets. So subnet 00, subnet 01, and subnet 10. And the 4th subnet, the 11, is the spare subnet. So as you remember, we go by step of 64 in the last byte. So 0, 64, 128. And when I have information about a subnet, I can compute its network address, its broadcast address, the first valid IP address, and the last valid IP address, no? So we have this first subnet, another subnet, and another subnet that we are using in here, no? Remember that the last subnet, this one, is a spare subnet. That's why it doesn't appear in this graphic. Okay, now if I want to configure the router, this router, I have to use this command, no? So for example, here we have an interface which is called gigabit Ethernet 0/0. The IP address will be 192.168.1.1, as we can see here, no? Here we have a serial interface, serial 0/0/0/0. The configuration is done here. And the IP address that we are going to assign to this interface is 192.168.1.129 that we can see here. Okay, so that will be the configuration of the Cisco router. So we'll come back to that in another class, no? So here there is a summary. Let's say that you have an original network, which is a /16. If you borrow only 1 bit, you can create 2 subnets. What will be the number of valid IP addresses in each subnet? So how many host bits is still left? 15, no? You borrow 1 bit, and 15 are left for the host bit. So this will be 2 to the power 15 minus 2. Okay, minus 2 because we lose the first IP and the last IP. Now, if you borrow 2 bits, how many bits are left for the host part? 14. So how many host IP address are you going to have in each subnetwork? 2 to the power 14 minus 2, which is this number. And how many subnets you can create? If I borrow 2 bits, I can create 4 subnets. Subnet 00, 01, 10, and 11. Okay? If you borrow 3 bits, you can create 8 subnets. How many valid IP addresses we will have in each subnet? Look at the number of host bits that we have. We have 8 plus 5, which is 13. So this will be 2 to the 13 minus 2. Okay? Let's take this example. If we borrow 6 bits from the host part and we convert them to network subnet part, how many subnets I can create? 2 to the power of 6. 2 to the power of 6 is 64. Now, how many valid IP address I will have? See, if I have 10 bits for the host part, it will be 2 to the 10 minus 2. And 2 to the 10 is 1024. And 1024 minus 2 will be 1022. Okay? This is another example. Let's say that the initial network is this one, 172.16.0.0/16. And you want to create 100 subnets. Can I create 100 subnets? Exactly? No. So what should I create? instead of 100. 128. So I will have 28 spare network, spare subnetwork. If I want to create 128 subnetwork, how many bits I need to borrow? 7 bits, isn't it? Look at here. On the third byte, they borrow 7 bits, and they convert them into subnet bits. So all this will be network, subnet, and this will be host. So if you borrow 7 bits, 16 plus 7 is 23. And 23 in the dotted decimal notation is 255.255.254.0. What will be the magic number? So I'm going to parse this IP address, this net mask, sorry, from left to right in search of the last byte that is not 0. This is the byte that is not 0, the last that is not 0. So 256 minus 254 is 2. So the magic number is 2 and is in the third byte, which means that when I'm going to create my subnetwork, in the third byte, I have to go by step of 2. So 0 plus 2 is 2, 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8, blah, 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 until the last one, which will be 254. So those will be my 128 subnetwork. Remember, we are not going to use all of them. We need 100, but we cannot do 100 exactly. So we do a little more, and we have spare network. So the company can increase in size, and we don't have problem because we still have, in this case, 28 spare network. No? So here they just say, if you borrow 1 bit, 2 subnetwork. If you borrow 2 bit, 4. So here, if I borrow only 6 bits, I can create 64 subnetwork. I need to create 100. So I cannot borrow only 6 bits. I need to borrow 7 bits. If I borrow 7 bits, I can create 128 subnetwork. And I can satisfy my requirement of creating 100 subnetwork, no? So here they show you the information of the first subnetwork. So remember, the magic number is here, and we go by step of 2, which means that if the second subnetwork is 172.16.20, this first subnetwork must end in which IP address? One IP address before this one. And what is one IP address before 172.16.20? 1.255. 1.255. Okay? So the broadcast address of this network will be 1.255. If you look at here, they say this will be the broadcast address of the first network. And of course, the last valid IP address is one IP address before this one IP address before 172.16.1.255 is 172.16.1.254. So for example, let me come back. Here, what will be the broadcast address of this network? This is the second subnetwork. It starts in 172.16.20 and go up to what? So it will be one IP address before 40. What is one IP address before 40? It will be exactly 172.16.3.255, correct. For example, this one started 172.16.40 and ended 172.16.5.255. Look at the last one, 172.16.254.0 up to 172.16.255.255. Okay? Okay, let's say we have another example here. We start with this network, 10.0.0.0/8. And we want to create 1000 subnetwork. Can I create exactly 1000 subnetwork? No, we can create what? What is the power of 2 that is closer to 1000 and is bigger than 1000? 1024, exactly. So we cannot create 1000 subnetwork, but we can create 1024. So if you look at the slides, the previous slides, it say if you borrow 1 bit, 2 subnetwork, 2 bit, 4 subnetwork, blah, 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 blah. If you borrow 10 bits, you can create up to 1024 subnetwork. So I need to borrow 10 bits. So of this 8 and these 2, I will change them from host to subnet bits. With 10 bits, I can create up to 1024 subnetwork. So look at the level of the mask. The original mask was /8. If I borrow 10 bits, 8 plus 10 is 18. So the new net mask for the subnet is /18. And /18 is this net mask in the dotted decimal notation. Let's find the magic number. So I'm going to parse this net mask from left to right in search of the last byte that is not 0. It is there in the third byte. It's 192. So 256 minus 192 is 64. So to go from one network to the next network, the magic number is in the third byte, and I go by step of 64. So look at 0 plus 64 is 64. 64 plus 64 is 128. 128 plus 64 is 192. 192 plus 64 will be 256. So since it's 256, I put 0 here, and I have a carry of 1. Now 0 plus 64 will be 64. You see how it's worked? So if I consider the first subnetwork, this one, what will be the broadcast address of this network? So it will be one IP address before the next subnetwork. So the next subnetwork starts in 10.0.64.0. What is one IP address before that? Exactly, it will be 10.0.63.255. So look at here, they give you the information of the first subnetwork. So that will be the network address, and that will be the broadcast address. So we can see 10.0.63.255. Okay? Okay. Let's do exercises now. So I'm going to go back to where we were doing. So if I remember correctly last time, we end in exercise 10, where we have a net mask inside our notation, and we want to convert it to the dotted decimal notation. So if I do /25, it will be what? 8 plus 8 plus 8 plus 1, isn't it? So 255.255.255.128. If I take this one, this is what? 8 plus 8 plus 7 plus 0. So 255.255.254.0. Okay? Okay, this exercise, you have the net mask in side down notation or in /. sorry, you have the net mask in dotted decimal notation. And they ask you the net mask inside our notation. So for example, this one, how many one is in this net mask? 8. Okay, so this will be /8. This is exactly the same as /8. What about this one? How many one we have? 3 1, isn't it? Because 224 is 1 1 1 0 0 0 0 0. So we have 3 1, and that's it. What about this one? 17, yes, correct. It will be 8 plus 8 plus 1. What about this one? 28, no? It will be okay. Okay, let me keep it like that. It will be 8 plus 8 plus 8 plus 4. Here we have 4 1. It's 1 1 1 1 0 0 0 0. Okay? What about this one? So in this byte we have 8 1. And in this byte we have how many 1? 5 1, correct. This is 1 1 1 1 1 0 0 0. So it will be 8 plus 5, which is 13. Okay? What about this one? This one will be what? /0. We don't have any bit that is in 1. What about this one? /32. All the 32 bits are in 1. Okay? What about this one? /16. 8 bit in 1 here in the first byte, 8 bit in 1 here in the second byte. So /16. What about this one? 8 plus 8 plus 8 plus 5. So it will be what? 29, no? So this is a /29. Okay? What about this one? Here we have 8, and here we have 6. So 8 plus 6, 1 will be what? 14. This is a /14. Okay? Okay, there is something that is called the wide card. So the wide card is when you have a net mask, you can compute the wide card by doing the 1 complement, which means that you change all the 1 in 0 and all the 0 in 1. So let me show you the wide card in one of the examples here. For example, we are going to take this one and I'll explain you over this one what is the wide card. So let me open Paint. Okay, so we have as a net mask, we have 255.248.0.0. We're going to put that in binary. So 255 is 81. 248 is 51. Of course, 0 is 80. And another 0 is also 80. So this is the net mask. The wide card you change the 0 in 1 and the 1 in 0. So you invert everything. So when I have a 1, I put a 0. I have here 1, I put 0. And I change the 0 in 1. So that will be the wildcard. You invert everything. So if you look, this byte is 0. This byte is 7. This byte is 255. And this byte is 255. So the wildcard associated with this one is 0, 7, 255, 255. And the wildcard have one property, that if you add the byte together, you will get 255, 255, 255, 255. So let's do that. Let's add up them. So that was the original net mask. Let me add 0 here, 7 here, 255 here, and 255 here. Let's do the addition byte by byte. So 0 plus 255 is what? 255. 0 plus 255 is what? 255. 248 plus 7 is what? 255. And 255 plus 0 is 255. So when you add the net mask with the wildcard, it's always 255, 255, 255, 255. Okay? This is called the wildcard. So it's very easy to find the wildcard. You just invert 0 in 1 and 1 in 0. Okay, so here they say that there are several methods. The first method consists of doing the 1 complement of the subnet mask. So you change every 0 bit in 1 bit and every 1 bit in 0 bit. The second method consists in subtracting from each byte the subnet mask from 255. This is what I was saying, that if you add up them, you will end up with 255 in the 4 bytes. Okay? So let's do, for example, F. So F is 255, the net mask is 255.255.192.0. What will be the wildcard associated? So I need to put a number here, such as when I add up them, the result is 255. So what should I put here? 0. 0 here. What should I put here? Such as when I'm going to add them up, I will have 255. 63, yes. And here, 255. So this is the wildcard. Okay? So look at the wildcard is a succession of 0 followed by a succession of 1. Because it's the opposite of a net mask. A net mask is a succession of 1 followed by a succession of 0. So the wildcard will be a succession of 0 followed by a succession of 1. Any question about that? Okay, let's go to the other exercises. So this is very similar to the previous one. Let's see that. A network has been assigning the following net mask. Oh, no, it's different. What is the total number of IP address in the network? Okay. So if I have a network that have this net mask, what is the total number of IP address in this network? And how do I compute it? So look at we have a network with a net mask. I will write NM for net mask, which is 255, 255, 255, 0. So how many IP addresses in total we have in this in a network that have this net mask? So how we compute the total number of IP addresses? 2 to the power of number of bits in the host part. How many bits we have in the host part here? 8 bits in the host part. So the number of IP addresses in this network will be 2 to the power of 8, which is 256 IP addresses in total. Now, if they ask you valid IP addresses, it will be 254 because we lose 2. So we can say the host part has 8 bits. So the total number of IP address will be 2 to the 8. And 2 to the 8 is 256 IP addresses in total. Okay? Very easy to answer. Okay, let's do B. So this time the net mask is 255.255.0.0. So in a network that have this net mask, what is the total number of IP addresses? Two to the 16. Okay, we have 16 bits dedicated to the host part, so it will be 2 to the 16, and 2 to the 16 is 65,536 IP addresses, no? Okay, let's do C. C, the net mask is 255.128.0.0. So how big will be this network? How many IP addresses we will have in this network? To the 23, yes. How many host bits we have? Look, this net mask is what? Is /9, isn't it? So 32 minus 9, which is 23, will be the number of host bits. 23 host bits. So the total number of IP addresses will be 2 to the power of number of host bits, 2 to the 23. Okay, you take a calculator and you compute that. This will be the number of IP addresses. This is a huge network, of course. Let's do D. D, we know that the net mask is 4/22. So what will be, it's even easier here. How many IP addresses I will have in a network like that? Sorry, how many? 2 to the 10, no? And 2 to the 10 is 1024, no? Or because this is a 4/22. 4/22 is, I should keep it 4/22. It's easier with 4/22. This is a 4/22, isn't it? So number of host bits, 32 minus 22. 10 bits that are dedicated to the host part. 10 bits for the host part. For the host part. So if I have 10 bits for the host part and each bit can take 2 values, the number of IP addresses that I will have is 2 to the 10. And 2 to the 10 is 1024 IP addresses. Okay? What about F? F is the network part, the network mask is 255, 255, 255, 255. And as you know, in side-down notation, this is what? /32. So how many host bits we have? 0. So the number of host bits will be 32 minus 32. 32 minus 32, which is 0. So 2 to the power of 0 is 1. This is a network that has just one IP address. Okay? When I use this mask, I'm creating a network with just one IP address. Let's do this one, O. So in O, the net mask is 255, 255, 192.0. So if I rewrite this net mask in the side-down notation, it will be what? /18. 8 plus 8 plus 2. 8 plus 8 is 16. 16 plus 2 is 18. It's a /18. So the number of bits in the host part will be what? Number of bits in host part. 32 minus 18 will be 32 minus 18. And this gives me what? 14, no? So the total number of IP address will be 2 to the 14. Okay? Okay. Convert the following net mask in side-down notation from net mask in side-down notation to the dotted decimal notation. Okay, we have done exercises like that. Exercise 3. A customer of an internet service provider is requiring a block of IP addresses to connect the following number of hosts. What should be the minimum size of the proposed network on the associated net mask? So somebody wants to connect 12 hosts to a network. What will be the minimum size of the network if I want to connect 12 hosts? I need 12 IP addresses, no? This exercise says I need 12 IP addresses. So 12 hosts is the same thing as I need 12 IP addresses. Can I do exactly 12? No. You can do 1 IP address or 2 IP addresses, 4 IP addresses, 8 IP addresses, 16 IP addresses, 32 IP addresses. So what will be the number that we choose in this case? 16. I have to do 16 IP addresses. I cannot do 12. So I'm going to give to the network administrator a network that is bigger than what he really needs, which is nice because if he bought new computer or new network devices, he still have spare IP addresses. So we cannot do 12, but we need a network of 16 IP addresses. Network with a total of 16 IP addresses. If I have 16 IP addresses, what will be the net mask of this network? which means the host part will have how many bits? If I have 16 IP addresses, the host part will have 4 bits. Exactly. The host part has 4 bits. If the host part has 4 bits, what will be the net mask? It will be a / what? 28, correct. It will be a / 28. On a / 28, if I write it in dotted decimal notation, will be 255, 255, 255, and what else? 240. Here, with this net mask, I can create a network with a total of 16 IP addresses. So I will satisfy the requirement of this network. This network needs to connect a total of 12 network devices, which means they need 12 valid IP addresses. Okay? Let's see the other question. 255 hosts. So this time, somebody come to me and say, I need 255 valid IP addresses, 255 host IP addresses. So what is the minimum size of network I will give to this person? $255. Remember that it have to be a power of 2. It can be 1, it can be 2, it can be 4, it can be 8, 16, 32, 64, 128, 256, 512, 1024, but it cannot be something that is not a power of 2. Okay, why it's a power of 2? Because if you borrow 4 bits, it's 2 to the 4. If you have 4 bits in the host part, sorry. If you have 5 bits in the host part, it's 2 to the 5 IP addresses in total. Okay, so I need 255 valid IP addresses. So what will be the minimum size of the network? Okay, number of IP addresses, 8 will be the number of host bits. So number of IP addresses will be what? Okay, with 256, how many valid IP addresses you have? 254. So this person is saying, I need 255 valid IP addresses. So if you give it a network with a total of 256 IP addresses, it will have 254 valid IP addresses. So this will not work for this person, no? So we cannot give it a network of 256 IP addresses because one of the device will not have a valid IP address. So one of the device will not be, I will not be able to assign it an IP address. So if I cannot do with 256, what should I choose? 512, exactly. So in this case, we need a network with 512 IP addresses. So we need a network with 512 IP addresses in total. So if I have 512 IP addresses, how many bits I have in the host part? Nine bits. So 9 bits in the host part, isn't it? If you have 9 bits in the host part, what will be the network mask? $23, exactly, which is 32 minus 9. 32 minus 9 is 23. If I put this net mask in dotted decimal notation, it will be 255, 255, 254, 0. Here you have 512 IP addresses in total. Valid 510. Okay, but we cannot use a network with a total of 256 IP addresses because we don't satisfy the requirement of 255 valid IP addresses. Because with 256, you only have 254 valid IP addresses. So of course, we are hosting a lot of IP addresses. Okay, we are hosting a lot here, but there is no way to do something better. We need to host. Okay, somebody say, I want to create a network and I have 33 devices that I want to connect into this network. So I need 33 valid IP addresses. So let's see what will happen with this need. So the person needs to connect 33 hosts or 33 network devices. What will be the minimum size of the network? 64. So the network must have 64 IP addresses in total. So how many host bits? 6, because 2 to the power of 6 is 64. 6 host bits. If I have 6 host bits, what will be the net mask? So 32 minus 6 will give me 26, /26. And /26 is 255, 255, 255, 192, which is 8 plus 8 plus 8 plus 2. Okay? It's okay with that? You understand it? Okay, let's see the next exercise. So, exercise 4. You are given the following network. How many subnet of size 124 IP addresses can you create in this network? So look, I have this network. And I want to know how many subnet of size 124 IP addresses I can create. So the question is, in this network, how many subnet of this size you can fit? So how can we compute that? How can we compute that? Correct. This is 2 to the 24 divided by 1024. So what is 2 to the 24? The total number of IP addresses that I have in this network. So I compute the total number of IP addresses that I have in this network divided by 1024, and that will give me the number of subnet that I can create, of subnet of size 124. So first, let's compute total number of IP addresses in the original network, of IP addresses in the network 9000/8. So in the host part, I have 24 bits. So the total number of IP addresses will be 2 to the 24, which is a big number. Now, I'm going to divide all this IP address in block of 1024. So the number of subnet will be 2 to the 24 divided by 1024. So this is what? 2 to the 14, isn't it? Because this is going to be 2 to the 24 divided to 2 to the 10. So 2 to the 24 minus 10. 2 to the 14. Okay, I can create 2 to the 14 subnet. 16,000 and something. You understand? Yeah? So this network here, 90004/8. So we have 24 bits dedicated to the host part. So the number of total IP addresses will be 2 to the 24. So this is the total number of IP addresses in this network. Now, if we divide this network in subnet of 1024 bits, we have to divide this, the total number, by the number of each subnet. And it will give us the number of subnetwork that we can create of this size. So we can create 2 to the 14 subnetwork of size 1024 IP addresses. Okay, here, B. The original network is 150.96.0.0/16. So how many subnets we can create from this network of size 1024 IP addresses? So it will be the same thing. Total number of IP addresses divided by number of IP addresses in a subnet. And this will give me the total number of subnets that I can create. So what is the total number of IP addresses in this subnet? In the original subnet? 2 to the 16, exactly. Total number of IP addresses in the original network, which is 150.96.0.0/16. So it will be 2 to the 32 minus 16, which is 2 to the 16. So now the total number of subnets will be what? Total number of IP addresses divided by the size of the subnet. Is it okay for everybody? So this will give me 2 to the 16 divided by 2 to the 10. 2 to the 16 minus 10, 2 to the 6. And 2 to the 6 is what? 64. You can create 64 subnets of 1024 IP addresses. Let's do D. So D, we start with the original network is 142.129.0.0. No, it's too easy. It's the same as B. So let's do E. So E is the original network is 20 .48.96.0/21. Okay, so first I need to compute the total number of IP in this network. So total number of IP addresses in the original network. This will be what? 2 to the power of 32 minus 21. And this will give me what? 2 to the power of 11, isn't it? And 2 to the power of 11 is what? 2048, if I want to compute it. Of course, if you have 2048 IP addresses, and each subnet are going to have 1024 IP addresses, how many subnets you can create? 2. Okay, so number of subnet that I can create will be 2 to the 11 divided by the size of the subnet, which will be 2 to the 11 divided by 2 to the 10. And this is 2 to the 11 minus 10 is 2 to the 1. And 2 to the 1 is 2, of course. If I have 2048 IP addresses, I can divide them in 2 blocks of 1024 IP addresses. Okay? Exercise 5. Let's see what we have here. You are giving the following network. How many subnets of size 128 IP addresses can you create in this network? So this time, we are creating subnets that are smaller than the previous exercise. So let's do this one. So we have this network, 192.3.24.0/24. And we want to know how many subnets of 128 IP addresses we can create. Oh, 199, you are right. Okay. So, what is the total number of IP addresses in this network? 2 to the 8, yes. Total number of IP addresses in the original network is 2 to the 32 minus 24. So it's giving me 2 to the 8. And 2 to the 8 is 256 IP addresses. Of course, they go from .0 to .255. So how many subnet of 128 IP addresses you can create? Total subnets. 2, of course. It will be 2 to the 8 divided by 128. And 128 is what? 2 to the 7. So it's giving me 2 to the 1, and 2 to the 1 is 2. Of course, if you have IP addresses that go from 0, blah, blah, blah. Let me put 127 here. 128, blah, 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 255. So this will be from 0 to 127, this will be the first subnetwork. And from 128 to 255, it will be the second subnetwork. It's why we say, you can create 2 subnetworks. The first one will go from 0 to 127, and the second will go from 128 to 255. Okay? Let's see what is coming. So Exercise 6. Given a host address on a subnet mask, you can use the bitwise ANDing operator to calculate the associated subnet address. In this exercise, you are required to first convert an IP address on subnet mask to their binary equivalent. Then you must do the bitwise AND between the host address and the subnet mask to get the address of the subnet. Finally, convert the binary form of the subnet address to its decimal form. Okay. So look, here I have this IP address that I put maybe in a networking device with this subnet mask. So this IP address belongs to which subnet or to which network? So as I put it in binary, it's a lot of time, put it in binary. We can do it, but it's a lot of time. We can keep it in decimal. Let's do one in binary. So for example, this one will be 1111, 1111 dot okay, this will be the net mask. Okay, 172 is what in binary? Okay, let's use the calculator. The programmer calculator, 172 in binary is AC. So 1010 and C is 1100. Okay. Then we have what? We have 16. 16 is what? 0010. No, 0001, 0000. Then we have 145. Let me do 145 here. So 145 is 91 in hexadecimal. So it will be 1001, which is 90001. And 29 will be in binary. Let's see. 29 will be 1D. So 0001, 1101. Okay. Everything is in binary. By the way, let me put them in another font. Console, which is easier. Okay. So if we do the bitwise AND, here the last byte will be what? Let's do the first byte first. What will be the result of the first byte? If you bitwise one, this value with this value. So the first one will be 1, then 0, then 1, 0, 1, 1, 0, 0. Correct. Then we have what? 0, 0, 0, 1, 0, 0, 0, 0, isn't it? Then we have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So the network is belong to which network? 172, 16, 0, 0. So remember that last time you are going to do bitwise AND between, let me put them in console as such. No, let me put them here. You are going to do 172, 16, 145, 29. Bitwise on 255, 255, 0, 0. We saw that when we have a byte bitwise AND 255, what will be the result? The original byte, no? When you bitwise AND with 255, you don't change the value. So here it will be 16 also. When you bitwise AND with 0, the result will be 0. So you see, this is the result. We have the same here, but we lose a lot of time here. We went to binary. We don't need to go to binary sometime. Okay? Let's do the second one. So let's put it here. So we have 192, 168, 10, 10. And we have to bitwise AND with 255, 255, 255, 0. What will be the result? So the first byte will be what? 192. Here it will be 168. Here it will be 10. And here it will be 0. So this IP address belongs to this network. 192.168.10.0/. Okay, we don't have. Yeah, we do have it. /24. It belongs to this network. Okay. More interesting is the third case. Let's do the third case to see, because the third case is not that trivial, no? So we have 192, 168, 68, 210. And here we have 255, 255, 255, 128. So what will be the first byte? $192, correct. Then 168, correct. 68. So here it's not that easy because we don't have 0 and 255. So just for this byte, we can convert it to binary and do it in binary. So let's see what is 210. So 210 is D2. So D is 1101 and 2 is 0010. This is 210. And 128 is 10000000. Let's do the bitwise AND. What will be the first bit? 1. Then all the other ones are in 0, isn't it? So this is what? 128. So here we have 128. But I just put in binary what I need to put. For example, here you don't need to go to binary. You are losing your time because you already know that the answer will be 192. Here you don't need to go to binary because the bitwise AND is 255. It will keep the 168. This one will keep the 68. This one you need to go to binary. So you go to binary. Of course, if you have a calculator in your hand, like we have, we do have the AND operator. So look at, here we have bitwise, you see? So I can say, let me clear first everything. I can say I want to do 210, which is this, bitwise AND 128 equal, and it's told me it's 128. So we did compute it correctly. Okay, so we do have the bitwise AND. We have the bitwise AND, the bitwise OR. This is the one complement. Okay. So please remember, start as soon as you can. Homework number 1. Okay? I'll see you next week.